Okay, so on Friday, we were talking about how gravity acts as a centripetal force and how that can cause a satellite to orbit the Earth. Okay, we talked about Newton's thought experiment, about the cannonball, okay, being fired from the top of a tall mountain, okay, and how, in principle, that idea is sound. In the practical sense, it just doesn't work because nothing can go that fast through the Earth's atmosphere. Okay, but the principles behind it, okay, are sound. If something is going to orbit the Earth, gravity needs to be pulling it back, but it needs to go fast enough that the distance it falls is equal to the distance the Earth curves away, so that its projectile arc does not ever encounter the Earth's surface. Everybody with me on that one? Okay, so that's kind of review what we talked about there. And then we looked at how we set this up in terms of a formula. And we said that we set this up in terms of a formula as this. The centripetal force is being provided by the force of gravity. Okay, but we couldn't do it this way. What was the reason for that? Right, we don't know what little g is at various points that are large distances from the Earth's center. Okay, we know what it is on the Earth's surface. It's around 9.81. But we don't know what it is at the different orbital heights that we might encounter. So this formula kind of breaks down for us. What this formula is good for, though, is illustrating what happens to the mass of the satellite. Okay, if I do any manipulating of this formula, what happens to mass? It cancels. And it cancels because all things fall at the same rate. And that is only dependent on how far they are from the center of the object they are orbiting. Okay, and of course the mass of that object. That is where this comes in. That's why we have to use this. mv squared over r equals big G times the mass of the satellite times the mass of, we'll say, the Earth here, but I mean, it's not always going to be the Earth. It could be the sun if we're talking about a planet, okay, or it could be Jupiter if we're talking about one of Jupiter's moons or something like that, okay, divided by r squared. Okay, so we said that what happens here is that it looks like there's three masses, but there's really only two. Okay, the mass of the satellite is on both sides because the satellite is the one moving in the circle. Everyone follow me there? Okay, so if I start manipulating for something in here, the mass of the satellite is going to cancel. And then I can start solving for other things. Maybe I'm looking for the orbital radius, which would be the distance from where to where? Right. Center of the Earth to the center of the satellite. Okay, it's always measured center to center. Remember that we said that's one of the few tricks that there can be. Okay, one of the few tricks is that I could give you the altitude of the satellite or the height above the surface, same thing. Okay, or I could ask you to calculate that, which means you'd either have to add or subtract the radius of the Earth as kind of a last calculation there. Okay, so the way this formula is set up right now, I could calculate V, I could calculate R, okay, something like that with this, given the information I would have, which would be the mass of the Earth, because I always have that, okay, mass of the satellite, doesn't matter anyway, okay, and I would have big G. So I'd either be looking for V or R. However, a question could do this. They could, instead of giving you V, they could give you the period of the satellite and say, calculate its orbital radius. What do I do now? So my givens are that I know the mass of the Earth. Okay, I'm looking for R. I don't know what it is. I don't have V. I have T. We'll just say it's, I don't know, 1.5 hours. Yeah, that's probably too short. Let's say it's 3 hours. Okay. I should probably put that in seconds, right? And this, if I'm using this formula, I need that in seconds. So that would be 3,600 times 3. 10,800. Okay. Why am I so worried about the period being in seconds? Well, velocity would be in meters per second, but what two things did I put equal to each other? They're both what? Forces, right? What are forces measured in? And what is a Newton? a kilogram meter per second squared. So my units for time have to be in seconds. My units for radius have to be in meters. Okay, so I'm dealing with big numbers here. So I have to remember that I can't use something in hours or days or years. It has to be in seconds when I'm using this formula, unlike Kepler, right? That was the nice thing about Kepler. Use smaller numbers. Okay, so this is the information I have, and they want me to calculate R. What am I supposed to do? Like, I can't even use this formula to like, it's not going to help me. I can't calculate V with that formula because I don't have, I got T, I don't have R. So I can't even use that. So what do? I substitute. Okay, that's what I do. I will have to substitute into this formula for V. I don't have V, but I have T. And I'm looking for R, which is in this formula. This is what I don't have, and I can't get it. So I'm going to substitute this formula in for it here. Okay, that eliminates something I don't know and brings in something I do know. Okay, that helps me. I know it's not going to seem like it helps me while I'm showing you how to do it, but it does help me. Okay, because otherwise it would be impossible. All right, so if I'm going to put this formula in for V, what do I have to do to it? I have to square it because V is squared in this formula. All right, so I'm going to square this formula. That's going to be 4 pi squared R squared over T squared. Everybody okay with that? Okay, so now I'm going to substitute that into this formula. Okay. Okay, put mass of the satellite back in there, and I'm just going to take this. Can I do that? Sure I can. Now, can I do a little canceling here? Yeah, because I got an R squared on the top and an R on the bottom. So do I need that R on the bottom anymore? And what happens to the squared on the top? It's not squared anymore. Okay. Okay, I just substituted in the formula, and now I can solve for R. Because I have everything else. The mass of the satellite's going to cancel. I've got mass of the Earth. I know what big G is because it's on my formula sheet, and I'm looking for R, and I have T. Okay, so I have everything now except for R. Right? And all I had to do was substitute another formula in for a variable in that formula before. Okay, you'll have to be able to do that. Okay, doing that substitution thing. This exact substitution is what you'll have to do. No, because I still don't have R. R's still in there, right? Even if I go 2 pi R F, I still don't have R. It doesn't help me, right? I can find F, but I'm still short something. Okay, so now I'm going to manipulate, and I'm going to try and find R. I'm going to get R by itself. The algebra here gets big, okay? It gets a little bit crazy. So I want to get all the R's together, because I got an R squared over here, I got an R over here, right? I want to get all the R's over here on the left. So what do I do with this R squared? Okay, so I'm going to multiply both sides by R squared. So it's canceled off over here. What's R times R squared? R cubed. Okay, now I got to leave that here, move everything else over. So mass of the satellite, we already said that's going to cancel. Okay, T squared, that's going to come over here. Okay, so it's gone. And then I'm going to divide both sides by 4 pi squared. All right, so now R cubed is by itself. I'm left with this. R cubed equals big G times the mass of the Earth times T squared over 4 pi squared. All right, am I done? Why is what? It was squared, but there was an R on the bottom. Right? Okay, so now I've got R cubed. Do I want R cubed, or I don't just want R? Okay, so what do I have to do? I have to cube root. Right? Okay, so there's my formula. So yeah, I mean, it's a little bit of hairy algebra, but it's not too bad. Okay, I had to substitute one thing and then I had to move stuff around. So when this is all said and done, okay, I'm going to have r equals the cube root. That's a 3. It's getting worse. Okay, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, that's the mass of the Earth, okay, times the period, 10,800 squared, divided by 4 pi squared. All right, I would not suggest entering this in one step with many brackets. Okay, I tried to demonstrate that to you last week and I royally screwed it up. Okay, it was a very poor decision on my part. I would suggest doing this a piece at a time. Okay, so I would maybe do like just the top first. Okay, so there's the top. I'm going to divide that by 4 pi squared. And you'll notice I bracketed that because if I don't, it'll do order of operations, which is not the same thing. Okay. All right, and then I've got to cube root that. So I got to go math 4 and then put my answer in. Okay, so there is my orbital radius. It is going to be, what is that? 1, 2, 3, 4, 5, 6, 7. So 1.1 times 10 to the 7 meters, okay, is going to be my orbital radius for that satellite. Okay, now I could have had another trick in that question and asked you what's the height above the Earth's surface, which means you would do what with that number? Right, subtract the radius of the Earth from it, okay, as an additional point on that. Okay, but I didn't do that on this one because I wanted to just show you that substitution thing that's definitely going to come up time and time again when we're doing satellite motion problems. Okay, questions on how that worked? Don't worry, we're going to get time to practice that. Okay, so things to remember about motions of planets and satellites. Anything that's orbiting something else, okay, the orbital velocity and the orbital period are independent of the mass of the satellite. In other words, the mass of the satellite always cancels. Okay, it doesn't matter how big or small that satellite is, whether it's an actual artificial satellite or a moon, it doesn't matter. At that altitude, it has to move at a certain speed or have a certain period. Okay, that is entirely influenced by the mass of the object being orbited and how far above it you are. Okay, velocity and period equations that we derived can be used for any body orbiting another. In other words, Kepler's nice because I get to use small numbers, but in the end, this always works. Okay, anytime something is orbiting something else, that works because the centripetal force has to be provided by gravity. Okay, Kepler's nice, but we rarely get the information we need to use it. Okay, because we have so much of the information that's in this formula as on our formula sheet already, this is more reliable. Yes, you have to use seconds. Yes, you have to use meters, but it's always going to work for any satellite. Okay, so we're going to go over a couple of examples here just to kind of work through it and make sure we understand what's going on, and then we'll see how we're doing. Okay, so this example here, we got the moon being 3.844 times 10 to the 5 kilometers from Earth. Has to be in meters. Dirty trick. Right off the bat, they're trying something stupid. Okay, but if you're reading through it really quickly, it's something you could miss, and then suddenly you're off by a factor of 1,000 or more. Okay, if we're dealing with exponents here. All right, so we want to change that right away. Times 10 to the 8 meters. All right, we want to determine the orbital speed of the moon. Have we done this already? Yeah, we did this a while back, actually. Okay, back when we were talking about universal gravitation, we did this one. All right, so what we have is that the moon is being kept in a circle by the force of gravity. If I want to calculate the speed of the moon, I can use this formula. I don't have to substitute. Okay, and that's going to be equal to big G times the mass of the Earth times the mass of the moon divided by the radius of the moon's orbit around the Earth, which they gave us. Whoops, squared. Don't forget that. Yeah, it doesn't matter which one goes first. Yeah, it makes no difference, especially since the mass of the moon is going to cancel anyway. Yeah. Okay, so mass of the moon then is obviously also over here. All right, I'm solving for V. What do I have to do with R? Multiply it over. Okay, when I do that, this R will go away, and so will the square. All right, mass of the moon, going to cancel. Okay, and what do I need to do now? Square root. Okay, so for us, our final equation here will be 6.67 times 10 to the minus 11, okay, our universal gravitational constant, times the mass of the Earth, 5.98, times 10 to the 24. That's what it is on our formula sheet anyway. Okay, and then divided by the radius they gave us, which is 3.844 times 10 to the 8 meters, not the kilometers number. Okay, it's about the same number we got when we did it the last time. We got 10,017 the last time. Okay, or sorry, 1,017. This time we got 1,018, and that's because we used a slightly different number here than we used before. Okay, everybody all right with that one? Okay, so I mean it's a bit easier when you don't have to substitute. Obviously, okay, you're just looking for V or you're looking for R, right, or something like that. Okay, anybody still need that one? Okay, I want you guys to try these two. Okay, in number one, you're looking for Neptune's speed. Okay, they give you the mass of the sun. That's important because Neptune orbits the sun. Okay, and Neptune is a satellite of the sun, right? And then they talk about the moons of Uranus. That is how you pronounce it. It is not Uranus. It's Uranus.
So when it says from the sun, are we just assuming it's for the center?
Yes, when it gives you the orbital radius, it is giving you center to center. Yeah, so yeah, that's a good question to ask. So in Neptune's average orbital radius, that's center to center. Okay, and yeah, so that's what you're looking for.
It's not in the center,
It would specify. It would say above the surface or altitude or height. Look for those three kind of key terms. Yeah. Okay, I'll give you a few minutes on those, guys. All right, so we got Neptune's average orbital radius. So they gave us R, okay, and it was 4.5 times 10 to the 12 meters, so quite a bit further than Earth. Okay, and we know the mass of the sun. Okay, 1.99 times 10 to the 30 kilograms. All right, what keeps Neptune in orbit as a centripetal force is the gravitational attraction between Neptune and the sun. Okay, so that means we have mv squared over r, okay, equals big G times the mass of the sun times the mass of Neptune divided by the radius of Neptune's orbit squared. All right, so we are looking for Neptune's orbital speed. So to get V by itself, I'm going to multiply both sides by R. That'll cancel off the square. Okay, divide both sides by the mass of Neptune. So it will cancel, which is good because they didn't give it to me in the first place. Okay, and then I'm going to square root. Okay, so I'll have that V equals the square root of 6.67 times 10 to the minus 11, universal gravitational constant, times the mass of the sun, 1.99 times 10 to the 30, okay, divided by 4.50 times 10 to the 12. Okay, so big thing here, guys, is to make sure that we bracket the things we need to bracket so our calculator doesn't try to be smarter than we are. All right, and then I got to square root that. All right, so Neptune has to move at 5,431 meters per second, or 5.4 times 10 to the 3 meters per second. Okay, actually, sorry, 5.43, because we have 3 significant figures there. So it's pretty fast, a little 5.5 kilometers per second. Yeah, that's quick. But you think about how far Neptune has to go, right? It takes over 200 years for it to make an orbit, right? Something like that, or 100 and something years. I can't remember what it is, but it's a long time. It's a long time. All right. Are we okay with number 2? Okay. All right. Weird name for a moon. I mean, it's nice when you only have one moon, then you know what to call it, right? The moon. But if you're around Uranus, Uranus has a whole bunch of moons, as do most of the planets. And there's actually, believe it or not, a naming scheme that goes along with naming moons around all the planets. Okay. So Mercury and Venus don't have moons, so there's no naming scheme for them. Our moon is actually known as Luna. Okay. And then we have around Mars. Mars is the god of what? War. Okay. Mars has 2 moons, Phobos and Deimos. They are the companions of war, fear and panic. Phobos is fear, right? If you have a phobia of something, you have a fear of it. Phobos is fear. Deimos is panic. Those are the 2 companions of war. Anything orbiting Mars that's a natural satellite would have to have a war theme to it. Okay. And that's the naming scheme for Mars. Jupiter has over 60 moons. Jupiter is named for Zeus. So all of Jupiter's moons are, unfortunately, named for the lovers of Zeus. And we haven't run out of names. Yeah, Greek mythology for you. Okay. Yeah. Saturn. Okay. Saturn is like god of the harvest and time. So everything there. He's the Titan. Okay. He's like the head of the Titans. So all of the moons around Jupiter have to be named for the Titans. Like the biggest one is Titan, and then all the others are other Titans from Greek mythology. Okay. Uranus. All of them, for some reason, are Shakespearean characters. I don't know why that came up as the naming scheme for Uranus, but it's all Shakespearean characters. Okay, so this is like from Midsummer Night's Dream. A lot of them are from Midsummer Night's Dream. There's a moon called Puck, and yeah, and then there's a few from like the Tempest and the Taming of the Shrew. Okay. No, it does not have one called Romeo or Hamlet. Yeah, but they're all Shakespearean characters. And then Neptune, everything has to do with water. So Neptune's biggest moon is Triton for the trident that Neptune would carry. Okay, and for Pluto, okay, Pluto's the god of what? The underworld, right? Pluto's the god of the underworld, and so all of its moons have to do with the underworld. So its largest moon, which some people pronounce Charon and some pronounce Charon, okay, is the boatman that takes you across the river Styx. Okay, if you've ever seen that, that's who Charon is. And then there's like Hydra and Styx, and they're something to do with the underworld. Okay, so that there's a naming scheme for all of those. So if you discover a new moon around a planet in the solar system, you don't get to name it whatever you want. You have to follow the scheme. Oh, probably quite a while ago. Although we are still discovering like small moonlets around like Saturn and Jupiter and Uranus and Neptune as our telescopes get better. When New Horizons went by, that's when we discovered Hydra and Styx and a couple of other small ones around Pluto. But yeah, so we are, discovering a few here and there, and we have to stick with the naming scheme. So, yeah. Okay. Another example here. So I got Landsat, which is an Earth imaging satellite that takes pictures of Earth's ozone layer and thus has a polar orbit because that's where the holes in the ozone layer are. Okay. So it takes another geological features. It orbits the Earth at a height of 912 kilometers. What am I going to have to do with that number? I have to add the radius of the Earth and convert it to meters, because it's in kilometers. Okay, so I'm going to take, to find the radius, I'm going to take 6.37, right? That's what it is on our formula sheet, 6.37 times 10 to the 6 meters, and I'm going to add 912,000 meters to that to get the correct orbital radius, okay, for Landsat. So that'll be 6.37, 6 plus 912,000. All right, so there's my proper radius, 7.282. Okay, times 10 to the 7. Right, it was 10 to the 7. No, 10 to the 6. Sorry. Okay, so there's my proper orbital radius. Okay, it orbits Earth, and we want to find its orbital speed and its orbital period. Okay, so if I want to find its orbital speed, I can just use the formula we used when we found the orbital speed of Neptune on that other question. If I want to find its orbital period, I got two choices. The way this one is set up, I could find its orbital speed and then use this formula. Okay, I could do that, or I could substitute that formula in and solve directly for t. In this case, it doesn't matter which one you do because you can do it both ways. The trick comes when I give you the period and ask you for the radius. You have to substitute on that because there's no other way to do it. You don't have enough information to do it any other way. Okay, so let's find out what the speed of Landsat is right now. So this would be the mass of the satellite times v squared times r, or sorry, divided by r, equals big G times the mass of the satellite times mass of Earth over the radius squared. So we're looking for v, so we're going to move r over, mass of the satellite's going to cancel. We're going to take the square root, same as we did before. All right, so v equals the square root of 6.67 times 10 to the minus 11 times mass of the Earth, 5.98 times 10 to the 24, divided by 7.282 times 10 to the 6. Whoops. Okay, so that satellite is moving at 7,400 meters per second. Pretty quick? Has to be. Okay? It's pretty close to the Earth too at that distance. All right, 7,400 meters per second. All right, now, if I want to calculate the period, okay, like we said, because of the way this one is set up, I can just use this formula now and manipulate for period. So period will be 2 pi r over v, okay, and I just plug in my numbers. So 2 times pi times 7.282 times 10 to the 6 divided by 7,400. Okay, so we could do it that way. All right, so it would take it 6,182 seconds to make one complete orbit. Okay, or we could have done the substitution and calculated it that way. Although on this one, given the way they asked it, this probably makes the most sense. Okay, rather than doing two separate big math calculations. Okay, everyone all right with that? Okay, are all satellite motion questions pretty much the same? They're always FC equals FG. So really, it's just a matter of I got to manipulate for this or I got to substitute for that.
So a question like this, and to ask for both, when you use significant digits, you're solving the period?
Yes. Yeah, I would. Yeah, because it would. If I was writing this question, it would have been a part A and a part B, and then we would use the rounded value, right, from in our part B calculations. Okay. I want you to try those two. Question number 2, I think you should use the substitution method for that one, just to get some practice with it. We could solve it without that in 2 steps, but I'd like you to try the substitution method for question number 2. Okay, so on number 1, we have the International Space Station orbiting the Earth at a height of 359.2 kilometers. What do I have to do with that number? I got to add the radius of the Earth and convert it to meters. Okay, so my true radius there will be 6.37 plus 359,200 meters. All right, so that gives us 6.7292 times 10 to the 6 meters for our actual radius. Okay, so we're looking for its orbital speed. Okay, again, it's a satellite, so the centripetal force is being provided by Newton's universal law of gravitation. mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Okay, multiply both sides by r, that cancels. Mass of the satellite's going to cancel. Squared is gone, okay, and I'm looking at this 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, okay, divided by our 6.7292 times 10 to the 6. Okay, and when we do that, we're going to get somewhere around this. They use slightly different numbers. Like the book has 6.38, I think, as the radius of the Earth. So they have slightly different numbers. I think they have 5.97 as the mass of the Earth instead of 5.98. So if you got a number that's close to this, okay, you're fine. Should have come out like this. Yeah, 7.7. Yeah, I guess we get the same number. It's close enough. Okay, we get 7.70. They get 7.69. Okay, so close. Times 10 to the 3 meters per second. Okay. All right, how many people have done number 2? Okay, do we need to go over that one too, or we just need a little more time on that one? More time? Okay. Okay, let's have a look at number 2 here. So we've got this X-ray satellite that takes pictures of high energy objects in the universe. In order to do that, it has to be a very long way from the Earth. Okay, this is not orbiting anywhere near the Earth. So we are looking for its orbital period. So we're looking for big T this time. Okay, we know the orbital radius is 100. Actually, we know the altitude. So we need to calculate the orbital radius by going 6.37 times 10 to the 6 plus 114. Okay, 593, and I'm converting that to meters by adding 3 more zeros onto that. Okay, so we'll calculate our true radius here. All right, so our true radius is 1.20963 times 10 to the 8. Okay, so nice big number. All right, if I'm going to calculate orbital period, okay, using the substitution method, then I'm going to have this. FC equals FG. And I'm going to have mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. And then I'm going to substitute this in for v. But in order to do that, I have to square it. So that's going to mean 2 squared is 4, okay, pi squared, r squared, t squared. So I'm going to punch that in to this formula like so. M times 4 pi squared r squared over t squared. So that is going to get rid of this r and that squared. And now I've substituted that formula in. Now I need to solve for t. Okay, so I'm going to multiply both sides by t so that it's on the top. Okay, actually by t squared because it's squared in this formula. All right, so it's gone from there. I'm going to multiply both sides by r squared, which is going to give me r cubed. Okay, and then I'm going to divide both sides by g times the mass of the Earth times the mass of the satellite. Now, mass of the satellite is going to cancel, so that'll be gone from there. And I will have big G times the mass of the Earth underneath here, and I will square root that in order to get t. Right? Yes, that is a lot of manipulation. Okay, but that's the way it goes when we got big formulas. So the period of the satellite will be 4 pi squared times our radius, which was like 1.2092 or whatever, times 10 to the 8. Okay, I'll put all the numbers in, and that's cubed. We have to remember that. Okay, divided by 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 24. Okay, so this is a big hairy mess going into the calculator. Okay. So 4 pi squared, okay, times, in brackets, our answer cubed. All right, so there's the top. I'm going to divide that by what's on the bottom. And then I got to square root that. Okay, so that is going to take 4.19 times 10 to the 5 seconds. Yeah, we're going to get, well, actually they got the same number, 4.19 times 10 to the 5 seconds. Okay. All right, everybody with me there? All right, so that's, I mean, that's seems like a long time when it's written that way, but if we divide that by, right, it's 116 hours. Okay, so it takes a long time. It's way beyond our geosynchronous satellites and stuff like that. It has to be a long way from the Earth, so radiation from the Earth doesn't interfere, okay, with its operation. Okay, making some sense? All right, I'm going to give you a 5-minute break here, and then we're going to work on a couple other ones here to do with that. Yep. Yes, you can. Yep. Okay, so we're trying to find the time of 1 year on Mars, okay, by setting FC equal to FG, which means we're looking for period. We're looking for big T here. Okay, so we're going to substitute in. We're going to have m 4 pi squared times r over t squared. So that means I've already done this part where I've done 2 pi r over t. I've squared everything, and I've plugged it in and canceled off the r on the bottom and the squared here. Okay, then I've got big G times mass 1 times mass 2. Well, let's say mass of the sun here. Okay, mass of Mars here, right, divided by r squared, because we have to remember, of course, that Mars orbits the sun. It's a satellite of the sun. So if I'm going to solve for t, I'm going to move t squared over here. Then I'm going to multiply both sides by r squared, which will give me r cubed. Okay, and then I'm going to divide both sides by big G times the mass of Mars times the mass of the sun. Mass of Mars will cancel here, and I'll have big G times the mass of the sun here, square rooted to give me t. All right, so yes, a lot of moving things around. Okay, kind of complex algebra on that one. So what I'll have is 4 times pi squared times the radius of Mars' orbit, okay, which they told me was 2.3 times 10 to the 11. And that has to be cubed, okay, divided by 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, the mass of the sun. Okay, so that should give me the period of Mars's orbit, but it'll give it to me in seconds. Okay, so we're going to have 4 pi squared times 2.3 E11 cubed. All right, so there's the top. Okay, I'm dividing that by the bottom, 6.67 E negative 11 times 1.99 E30. And then I'm going to square root that. All right, so there's the period in seconds. I think that's what they got, right? Yep, 6.0 times 10 to the 7 seconds, or 1.9 years. All right, could I have also solved that using Kepler? Yes. Okay. I could have easily solved that one using Kepler because I could have used all of the Earth's information. They gave me the radius of Mars's orbit in meters. I could have used the Earth's orbit in meters and solved this using t squared over r cubed equals t squared over r cubed. Could have done it that way as well. Okay. All right, so expect that tomorrow's quiz will contain some satellite motion problems. Also remember that your circular motion assignments are due tomorrow. Okay, make sure that they are done, ready for the beginning of class, please.